Intermolecular forces to some of the physical properties of a liquid. So we'll talk about boiling point, viscosity, surface tension, and vapor pressure. Before I do that, I do want to do a quick review of our intermolecular forces. So the first one, and these are in a slightly different order than I did them on the last video, but hydrogen bonds. And we said hydrogen bonds were very specific. I have to have an oxygen, nitrogen, or fluorine, and those have to have a lone pair of electrons on them. And then the oxygen, nitrogen, and fluorine have to be bonded to a hydrogen. So we must have an OH, an NH, or an FH bond. And the oxygen, nitrogen, or fluorine must have a lone pair of electrons. We had dipole-dipole forces. And we said these exist between polar molecules. So we need to determine if the molecule is polar or not. If it is polar, it's going to have dipole-dipole forces, right? That's where the partial positive of one molecule is attracted to the partial negative end of a neighboring molecule. So the partial positive end, sorry, I forgot that word, of one molecule is attracted to the partial negative end of a neighboring molecule. If it's not polar, you're not going to have partial positive and partial negative ends of the molecule. You could bonds, but again, these are molecules. Our third one were London dispersion forces. And we said this one was due to a spontaneous induced dipole, that they're temporary. They tend to be pretty weak, but we do form and break them all the time. We said the bigger our atom or molecule or whatever it is we happen to be looking at is, right, the more electrons it has, the stronger these dipoles. I'm not going to write the whole definition again because it's kind of long, but these were the ones where electrons can be they're moving, right? And if they were bunched up on one side of the atom and that gets close to a neighboring atom, those electrons are going to cause the neighboring electrons to repel. So you end up with a partial negative on one, a partial positive on another, and those are attracted to each other. Because the electrons are constantly moving, however, we're making and breaking those induced dipoles all the time. So this was the one where we said if we have electrons, we're going to have London dispersion forces. The more electrons we have, the stronger the London dispersion forces. So these exist between polar and non-polar molecules. This was the one where I said, I won't give you something that doesn't have electrons. So even if you have no idea what the answer is, always write down London dispersion forces and you're going to get some credit. So between polar and polar molecules, between non-polar and non-polar molecules, if I was to mix you up and give you a polar and a non-polar, it would exist between those also. And it doesn't just have to be a molecule, it could be an atom, right? Between neon and neon. They'd be pretty weak because neon's small without a lot of electrons, but I would have London dispersion forces. So we said larger atoms, molecules with more electrons that are easier to distort. And our word for that is that they're polarizable. If something was polarizable, it has a lot of loosely held electrons that are easy to distort. So we can have induced dipoles pretty easily if something is polarizable. So these have stronger London dispersion forces. And then we also said that if it has more surface area, but the same size, right? And we went into more detail in the last video again. So same number of electrons, but more surface area, then that's going to have stronger London dispersion forces also. So our three types. We could actually add the dipole-dipole. The more polar it is, the stronger the dipole. I didn't leave much room, but we could add that. More polar, stronger dipole-dipole force. So something like oxygen bonded to hydrogen is going to have a stronger dipole-dipole force than nitrogen bonded to hydrogen one. So if we're looking at a substance's boiling point, and we talked a little bit about this in the last video also, right? I was comparing the boiling point of chlorine to bromine, right? Bromine's a liquid at room temperature. Chlorine's a gas at room temperature. So at 25 degrees Celsius, which is what room temperature is considered, we've already added enough energy to break the connections between the chlorine molecules, but not between the bromine molecules. So boiling point is definitely related to the strength of intermolecular forces. So boiling point, right? At our boiling point, our liquid is forming a gas. And honestly, at that point is actually in equilibrium. The gas is going back to a liquid. So the point at which it condenses is the same point at which it boils. It's just generally, if we're talking about boiling, we're talking about going in the forward direction. But what we're doing when we do that is we're breaking, right? When a substance goes from a liquid to a gas, the intermolecular forces are broken, right? We talked about that in the beginning of this chapter. We said that one of the defining differences, or the defining difference between a gas and a liquid, is that gases, I don't have any connections between particles. In liquids, I do, right? Those connections are my intermolecular forces. So when I'm going from a liquid to a gas, I'm breaking intermolecular forces. So the stronger those forces, the more energy I need to break it, the higher that boiling point. So stronger intermolecular forces means I need more energy to break those connections so a higher boiling point. So an example for us, we are going to rank the following in order of increasing boiling point. So we want the lowest one first, going to the higher boiling point. So our examples, let's look at, I don't know, C4, H10. Sorry guys, I'm just making these up as we go. Let's do helium. PF3 and HF. So essentially what we're saying when we say rank the following in order of increasing boiling point, what we're saying is rank the following in order of increasing strength of intermolecular forces, right? Because stronger intermolecular forces are going to give me a higher boiling point. So I want to know which ones have the weakest forces and rank them to the strongest forces. remember, to do that, we have to determine if they're polar or non-polar. So this first one, C4H10, it only has carbon and hydrogen, and if we remember, our non-polar bonds were things between it and itself, so like a carbon-carbon bond or a hydrogen-hydrogen bond. And then also carbon and hydrogen, well, it had an electronegativity difference. It was so small that we were saying it didn't really matter. We're just going to consider it non-polar because the little bit of polarity it has isn't going to affect the polarity of the molecule. We also said phosphorus hydrogen and carbon phosphorus were also non-polar bonds. So because this molecule only has carbon and hydrogen in it, right, the only type of bonds I can have are between carbon and carbon, which is non-polar, and between carbon and hydrogen, which is also non-polar. This molecule is right off the bat just non-polar. I don't even have to draw it out. If I give you something that's just carbon and hydrogen, it's always going to be non-polar for us. I could give a C100H202. Who cares what it looks like? It's going to be non-polar because it's just carbon and hydrogen. So it's always nice when you're given that. Like at first, it's like, ugh, how do I draw that? You don't have to. So just carbon and hydrogen is going to be non-polar. Helium is just an atom. There's no bonds, so it can't be polar. So just non-polar. PF3, this one we're going to have to draw. And again, this is going to be good practice for you guys to go back because I'm going to just draw it to give you the answers. But this one's Trigonal Pyramidal. Remember, we have to be able to draw the Lewis structure and then figure out the molecular geometry. It's a really ugly one, but it is Trigonal Pyramidal. If I was to assign bond dipoles, these fluorines are more electronegative than phosphorus. So I have 3 polar bonds. I don't have one counteracting it, so this is a polar molecule. And again, if you need to go back and review that, that was back from chapter 4 and 5. Please do, because it's hard to do a problem like this if you don't know if the molecules are polar or not. HF is just one bond. It's not on the list of non-polar bonds, so that makes it polar. I will draw it out. There are lone pairs on that fluorine. The next thing I'm going to do is I'm going to list what types of intermolecular forces they have. So if it's non-polar, it's only going to have London dispersion forces. This is also nonpolar, so only London dispersion forces. I'm going to get these out of the way. This has London dispersion forces because we're always going to write that down. It's polar, so dipole-dipole. And then it doesn't have hydrogen bonds. Remember, to have hydrogen bonds, if we go back up here, I have to have an OH, an NH or an FH bond, and then a lone pair of electrons on those atoms. I have a phosphorus bonded to fluorine, so I don't have hydrogen bonds. HF, London dispersion forces, it has electrons, it's polar, so dipole-dipole. And then I just erased it, but I do have an FH bond, and I do have lone pairs on fluorine, so this also has hydrogen bonds. So of these, which one's going to have the smallest boiling point? Well, both of these, right, just have London dispersion forces, but we did say that bigger atoms with more electrons are going to have stronger London dispersion forces. So C4H10 is going to be bigger than just helium. So helium is going to be my smallest as far as boiling point. So bigger than that, I'm just going to use a less than, greater than sign, C4H10, right? It just has London dispersion forces. PF3 has London dispersion forces and dipole-dipole. And then HF has all 3 of them. So that is going to have the highest boiling point. So rank them in order of increasing boiling point, right? What we really mean is to rank them in order of increasing strength of intermolecular forces. The next couple we're going to look at are going to be very similar to that. So this next one is viscosity. And viscosity is defined as a substance resistance to flow. So if you were to like pour it, does it flow really well or does it not flow very well? If it doesn't flow very well, then it has a higher viscosity. So it's a substance's resistance to flow. And it's related to the strength of the it's related to the strength of the substance's intermolecular forces. If they're strong, then the individual particles can't move around very well. If they're weaker, then they can move around better. The more the individual particles in the liquid can move around, the less it's going to resist flow. So it's related to the ease at which individual particles in the liquid can move around. If they can move better, they flow better. If they cannot move as well, they flow not as well. They're going to have a higher viscosity. So stronger intermolecular forces more resistance to flow, so higher viscosity. So if I was to go back up to this last example and say rank the following in order of increasing viscosity, I'm going to get the exact same answer, because what I'm really saying is rank them in order of increasing strength of intermolecular forces, right? The stronger the intermolecular forces, the higher the viscosity. The stronger the intermolecular forces, the higher the boiling point. So those two are going to coincide with each other. The next one we're going to look at is surface tension. And our trend is going to be the same as it is for viscosity and boiling point. Our definition, though, however, is different because it's a different property. So surface tension is defined as the resistance of a liquid to spreading out and increasing its surface area. So the resistance of a liquid to spreading out and increasing its surface area. And it's also this one is also due to intermolecular forces, and it's due mostly to a difference felt in intermolecular forces between the surface molecules and the interior molecules. So if I had a liquid, and I'm just gonna draw just a drop, let's say we poured liquid onto the top of my iPad and have this drop of liquid. These particles that are on the outside, right, so these dots are representing my particles, and then these particles are the ones on the inside. The ones on the inside are actually surrounded by other particles. Let's use a different color here. So they feel more intermolecular forces than the ones on the surface do, because these ones on the surface only feel connections between neighboring particles and the ones below it, where all these ones in the middle are surrounded and they feel a lot more intermolecular forces. Intermolecular forces are stabilizing. The more they have, the more stable it is. So a substance wants to have a lot of those connections. It's good for it, right? It's more stable. So these ones in the middle versus the ones on the surface are more stable than the ones on the surface, right? If those intermolecular forces are strong, then that difference is more pronounced, and it doesn't want to spread out and have less interior molecules and more surface molecules, because it's overall kind of decreasing its stability. If those forces are weak, then it doesn't really matter, because the difference between the surface molecules and the interior molecules is not that pronounced. So kind of writing some of that into words. The interior molecules or particles are surrounded by other particles, so they experience more intermolecular forces then the surface particles which only have connections to the particles below and next to them. So the interior particles are surrounded by other particles, so they experience more intermolecular forces than the surface particles, which only have connections to the particles below and next to them. Intermolecular forces are stabilizing, so a liquid wants to maximize the interior particles and minimize these surface particles. And that is our surface tension, right? We go back up to our original definition, the resistance of a liquid to spreading out and increasing its surface area. The reason it wants to do that is it wants more interior molecules and less surface molecules, because the interior ones are more stable because they experience more intermolecular forces. The stronger the intermolecular forces, the more pronounced the difference in stability. I'm writing a book here. Between the surface and interior particles is. So, more resistance to spreading it out, higher surface tension. So the stronger the intermolecular forces, the more pronounced the difference in stability between the surface and interior particles, so higher surface tension. So if we went back up to that original example and I changed the wording again that said rank the following in order of increasing surface tension, my answer is going to be exactly the same, right? Stronger intermolecular forces, the more I want to minimize those exterior ones, maximize the interior ones, the more I'm going to resist spreading out and increasing my surface area. So far we've had, right? If I have stronger, so I'm just doing an arrow up for stronger, higher intermolecular forces, I'm going to have a higher boiling point, I'm going to have a higher viscosity, and we're also going to have a higher surface tension. So given a few molecules, figure out if they're polar and nonpolar, determine what types of intermolecular forces they have. The more intermolecular forces, higher boiling point, higher viscosity, higher surface tension. The next one we look at, our trend is actually going to be the opposite. So this is the only one we're going to have where the higher the intermolecular forces, the stronger the intermolecular forces, the lower this property. And this one is going to be vapor pressure. Abbreviated P-vape subscript. And this one, I'm going to kind of draw a picture as we try to explain it. So I have a beaker and I have a liquid in it, and then I'm going to put a lid on it so it's closed. And what happens is these particles, right, that are on the surface are going to evaporate. Let me actually draw my liquid a little bit lower, it'll be easier to see it. So my liquid particles are actually going to evaporate, right? They're breaking their intermolecular forces, and I'm forming a gas, right? I have no intermolecular forces once it evaporates, right? I'm going from a liquid to a gas. So these gas particles are building up. I have a lid on it, however, so they can't go anywhere. So as it evaporates, I get more and more gas particles. Remember, pressure is defined as the forcefulness of those collisions, right? If I have more particles, I'm going to collide more often, my pressure is going to go up. So kind of our definition, it's the pressure felt in a gas above a liquid in a closed container. So our liquid's evaporating, those gas particles have nowhere to go. The more gas particles I have, the higher the vapor pressure, right? They're gonna collide more often if I have more gas, right? Increase your number of moles, you increase your pressure. So what happens is if we have weaker intermolecular forces, right? So my connections are not very strong, it evaporates more readily, so easier. Which means we have more gas, which means we're going to have higher vapor pressure. So weak connections, it evaporates easily, there's more gas, there's more collisions, there's higher pressure. And then of course the opposite is true, right? Stronger intermolecular forces, it doesn't evaporate as easily, less particles, lower pressure. So for this one, if I have stronger intermolecular forces, I'm going to have lower vapor pressure. Right? If we wanted to be complete, we could go back and add it to this list, though I've run out of room. Lower vapor pressure. So this time, if I was to go back up to this example and have you rank them in order of increasing vapor pressure, it's actually going to be the opposite. So helium, even though at a gas it's going to be at room temperature is going to be a gas. If we could have it in its liquid form, it would have to be in a tank under a lot of pressure. So it wouldn't be evaporating. So that one's even kind of hard to do. But if we were to do this one, it's going to have my higher vapor pressure. It's going to evaporate pretty easily. This is butane. If we are to just pour butane on the table, it just evaporates pretty easily. So if I was to do that in a closed container, I'm going to have a lot of gas particles. I'm going to have a lot of pressure. So let's do just one more example where we're doing them opposite. And it's good practice too. It'll give us something different. So actually, let's do CH3OH. I'll help you draw that one. Well, I'm going to draw all of them, but that's one that I wouldn't have expected you to be able to draw until after this little explanation that I'm going to give you. So CH3OH. Let's do ammonium. What else should we do? Let's eraser. Let's do OF2. And let's just do those three. So this first one, I know that hydrogen can never have more than one bond. We know that for sure, right? It can only have 2 electrons. It only has electrons in the first shell. In the first shell, I only have 1 orbital, and that orbital can only have 2 electrons. So I know that they have to be on the outside, which means my carbon and my hydrogen have to be bonded to each other. And then when it's written this way, it's giving us a clue. It's saying that on that carbon, I have 3 hydrogen. And then on this oxygen, I have a hydrogen. And then if you were to go figure out the total number of valence electrons, go through our rules, we end up with 2 lone pairs on that oxygen. So this would be my Lewis structure for it. Drawing its shape, because it has 2 central atoms, you actually look at them separate. So this the CH3 group, it has 4 bonds, right? 4 electron groups. Let me just highlight them. 1, 2, 3, 4. So it's tetrahedral. And it's going to that oxygen. So if I'm just looking at the carbon, that's its tetrahedron. If I look at, you get a different color highlighter here. If I look at my oxygen as my second central atom, it also has 4 electron groups, 1, 2, 3, 4. So tetrahedral electron domain geometry. But 2 of them are bonds, 2 are lone pairs, so this one's bent. It doesn't really matter where you want, which positions you make the lone pairs and which positions you make the bonds, but it is bent. So this one is polar. I have a bond between carbon and oxygen, which is polar. I also have a bond between oxygen and hydrogen, which is also polar. Because it's bent, and the strength of my carbon-oxygen bond is actually different than my strength between my oxygen-hydrogen bond, my molecule is going to be polar. So this one is polar. NH4, if we draw that one out, go through your Lewis structure rules, we end up with nitrogen in the middle, 4 bonds to hydrogen, or you should say 4 bonds each to a different hydrogen, otherwise it sounds like hydrogen has 4 bonds. I end up with this tetrahedral structure. I do have a formal positive charge on nitrogen. This one's nonpolar, it's symmetrical, even though it has polar bonds, right? Nitrogen is a little more electronegative than hydrogen, so it gets my partial positive. Sorry, nitrogen gets a partial negative. So it has 4 of these, but because it's symmetrical, they're going to cancel each other out, and it's nonpolar. And again, if you need to go back and practice drawing these, like just take these structures and try to draw them on your own. OF2, if I draw the Lewis structure, I have a bond to each of those fluorines. The fluorines have 3 lone pairs each, and then my oxygen, my central atom, actually has 2 lone pairs on it. So this one is bent also, right? The basic tetrahedral electron domain geometry, but 2 from our lone pairs. Fluorines are more electronegative than oxygen. Because it's bent, they're not going to cancel each other out, right? It's not symmetrical, so this is polar also. So the type of intermolecular forces it has, London dispersion forces, it has electrons, dipole-dipole because it's polar. And then the question is, does it have hydrogen bonds? It does, right? I have an oxygen-hydrogen bond, right here, oxygen-hydrogen bond, and then I have a lone pair on those oxygen, or on that oxygen, so I also have hydrogen bonds. Ammonium ions, nonpolar, just London dispersion forces, and then OF2, polar, it has London dispersion forces and dipole-dipole. Does it have hydrogen bonds is the question. I have oxygen with lone pairs, but that oxygen's not bonded to a hydrogen, so no hydrogen bonds for this one. So let's rank these ones in order of increasing vapor pressure. And be careful how I ask the question. I could say decreasing also, so do pay attention to if I'm saying increasing or decreasing. So when I say increasing, I want it to get bigger as I go. So I want the smallest vapor pressure first, the highest vapor pressure second. So remember, this is the one where the weaker the connections, the higher the vapor pressure. So I'm going to put the stronger connections first. So CH3OH, which is methanol, is going to have the lower vapor pressure. my OF2 is going to be next, and then ammonium ions are going to have the highest vapor pressure.